Hello and welcome back. For this video we're going to show some of the basic key features of polynomial functions, especially those that go past a second degree. For our objectives here, we're going to try to identify the x-intercepts, but we got to make sure they're in factored form. We're also going to determine the maximum number of turns possible by a polynomial function, and we're going to go from the graph, determine the number of real zeros from a polynomial function, state the end behavior of the function by analyzing the degree and the sign of the leading coefficient, and the leading coefficient is key here. And then of course we're going to try to create a rough graph of a polynomial function by hand, but again we're going to try to keep that in factored form because when it's not in factored form it becomes very difficult. The first thing we want to do here is try to recognize some patterns forming. The graph in the upper left hand corner is a linear, it's a first degree function. The one in the upper right is a quadratic, that is a second degree function, meaning its highest degree is 2. The bottom left is a cubic, it is a third degree function. And the bottom right is a fourth degree or a quartic function. And the first thing you might notice is the ones on the left hand side, the first and the third, these two right here. The arrows on either end of our graph are going in opposite directions. So when we want to analyze the end behavior of a function by looking at its degree and the sign of the leading coefficient, the degree, first degree and third degree, which are odd degree functions, have arrows going in opposite directions, whereas the second degree and the fourth degree functions have arrows going in the same directions. But what you might notice is the right hand arrow, let's see, the right hand arrow, so this one and let's say this one over here, they're all going up on those. And if we look at the sign of the leading coefficient, the reason those are going up is because the sign of the leading coefficient is positive. If we look at the right-hand arrow of the second degree here, that one's pointing down. And the reason that one's pointing down is because the leading coefficient is negative. So your end behavior depends on a couple of things, and that is your degree, what degree is it, and the sign of the leading coefficient. It will tell you what the right-hand arrow is actually doing. Another generalization here we can make is if you look at the first degree, which is right here, you'll notice it has no turns in the graphs. So a first degree has 0 turns. If we look at a second degree, it has 1 turn. If we look at a third degree, it has 2 turns. And a fourth degree has 3 turns. So the maximum, not any given time, but the maximum number of turns will always be 1 less than the degree of the polynomial. Another thing we wanted to determine was the number of real zeros. Well, the degree of the polynomial tells you how many solutions or how many zeros it will have at all times. But a real solution only occurs when we cross an x-intercept like this. So a first degree has, in this case, 1 real solution. The second degree has 2 real solutions, and a third degree has 3 real solutions. And if we look at the fourth degree, it has 1, 2, 3, 4 real solutions. However, let's take a closer look at that fourth degree. What if the fourth degree came down like this, went up, came back down, and then went back up? If that were the case, it would have only 1, 2 real solutions. The other 2 solutions would not be real. They'd be called complex or imaginary solutions. So the number of x-intercepts is the number of real solutions that the polynomial or the function will have. So let's take a look at this first function here. First you'll see the top part right here. That is the standard form of this function. So we could easily replace f of x with a 0 and we call that a standard form. Well, that's a cubic, and the reason we know it's cubic is because the largest degree on here is a 3. But in order to graph it, we want to put it in its factored form. Now its factored form looks like this. So if I were to FOIL or multiply that all out, this will end up looking like the top part. Now the reason that we put it in the factored form is when we want to solve for these zeros. So if I put a 0 right here in place of f of x, this first root right here would give me a -2 for a solution. And if you look at the graph, there's a -2 right there. And this next binomial, this next factor, if I set it equal to 0, would give me a +3 for a solution. And if I look at the graph, you'll see there's a +3 right there. And the third one right here, if I set that equal to 0, will give me a -5. And again, we'll look at the graph and we'll see that it actually does cross the x-axis at -5. So when we go to hand sketch these, we want to know where those places are that it crosses the x-axis. And we set all those factors equal to 0, and then we solve. Now we might also notice that the y-intercept down here is negative 30. And don't forget, the y-intercept always occurs when you put a 0 in for x. So if I put a 0 in for x here, here, and here, what I end up getting is my y-intercept is 2 times negative 3 times 5, which will equal negative 30. So we can actually identify the y-intercept as well on our graph. So we can identify the real roots by using the factors. We can also substitute a value in for 0 and multiply what's left over to get the y-intercept. Now the next thing we want to find out is what degree is our polynomial. Now we knew that this was a third degree because it had a 3 right up here. But if we're looking at it in factored form, how do we know if it's a third degree or a fourth degree or fifth degree? Well, we take the x in each one of these and we multiply them together. So x times x will give you x to the third power. So we have a third degree. If I happen to have a, let's say a 3 for whatever reason on the x inside there, then x times x to the third would give me x to the fifth, and I'd have a fifth degree. For now, we just have an x to the third. So since we have a third degree polynomial, we know that the arrows have to go in opposite directions. So we can see on the graph they're going in opposite directions. But how did we know that the arrow on the right-hand side actually went up? Because when we multiplied the x, and the x, and we got x to the third, the leading coefficient out in front of that, which is a positive 1, well, that was positive. And the leading coefficient tells you what the right-hand arrow is going to do. A positive points up, and a negative points down. So since the right-hand side is positive and points up, and this is a third degree, the left-hand side has to point in the opposite direction, which would be down. Okay, so here's a polynomial in factor form, and we're going to try to do a rough sketch of it. First thing we want to do is find out what is the leading coefficient. And the leading coefficient is going to be x times x times x times x times 2. And we'll see x times x times x is x to the fourth times negative 2 is going to give us negative 2x to the fourth. So our leading coefficient is actually just the negative 2. However, the 4 is important because the next thing we have to find is the degree. So the degree of our function is 4. So those two numbers tell us something important. The negative 2 will tell us that the right-hand arrow is actually pointing down. So let me do a little sketch here. So this is our x and our y. So the right-hand arrow will end up pointing down. And because our degree is 4, and that's even degrees have arrows pointing the same direction. So the left-hand arrow will point down also. So our end behavior will look something like that. So down on the right, down on the left, and then we got to figure out what's going to go on in between. So let me go ahead and draw a larger x and y axis. What we're going to do is we're going to get each of the roots or each of the zeros. So if we look at this first factor, x plus 1, we set it equal to 0, and we solve and we get negative 1. So let's call this negative 1, and this will be our first root. Let's look at this next one here, x plus 4. If we set that equal to 0, we get a negative 4 for our root. So 1, 2, 3, negative 4. And we have another root or another 0 at that point. The next binomial, we set that equal to 0. That factor is equal to 0. And we get a positive 2. So positive 2, there's our other root. And then our last one, we set that equal to 0. We get positive 3, like this. And one more thing I want to calculate real quick is what is my y-intercept? Now, you don't have to do this in most cases, but we might as well go ahead and do it. Our y-intercept is going to be when we put a 0 in place of all the x's. I'll put a 0 here, 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 and here. And what will happen is I'll get negative 3 times negative 2 times 4 times 1 times negative 2. And that value will come out as our y-intercept. So our y-intercept ends up equaling negative 48. So if I were to go to the graph, I'd go way down here at the bottom. We'll call that negative 48. And just the graph doesn't have to be perfectly to scale, so just want to show what it looks like in general. Now remember, we have a leading coefficient that's negative. That means my right-hand arrow is going to be pointing down. So my right-hand arrow is going to be pointing down this way. And because it's an even degree, my left-hand arrow is going to be pointing down this way in the same direction. And all I got to do is follow the path backwards. So I'm going to go up through the first root. I don't know how high I'm going to go, so I'm going to do a little squiggly mark like this and go down a little bit lower and come back up. Go back through this root. Don't know where that's going to go. Comes across and then comes back down. And my graph should look something like this. So here's that same graph. I put this through Desmos, and you can see what it looks like. -4 intercept, -1, +2, +3, and a -48 y-intercept. Down on this side, and I was correct. This side was a little bit higher up on the graph because the space between these two roots was greater than the space between these two roots. You also notice the space between here is a little bit greater, making this dip be a little bit lower than this side. So that's something you want to keep in mind when sketching these things by hand.